So when we got together again, or when we got together before, we talked about the middle school pizza problem. And I likened that to this conversation here, these angle relationships. Can anybody summarize that for me? Do you remember what I meant? What are we talking about with the middle school pizza problem? Did I tell that story? Yeah, about sharing. Yeah. So chances are when you order pizzas, especially if you order a bunch for a pizza party for middle school, whoever's cutting them up is not really being real careful, right? They cut and spin and cut and spin and cut and spin. And chances are you get a pizza that's cut a little bit unevenly. So if I'm the teacher passing it out to the middle school and I'm watching somebody that, no, you can go first. Why would somebody let somebody else go first in line in the pizza? Because they're like, I'm trying to figure you out, lady, and I'm thinking I want that bigger slice. And little does that person know that I'm figuring him out. Usually it isn't him, sorry.
That's like
Guys are hungry. What are you gonna do, right? So he's coming up, and I'm gonna on purpose, and I'm that kind of mean, scary teacher where I'm on purpose giving this piece of pizza to the nice kid. Why? What am I hoping that nice kid's gonna do? Share. Yeah, that's okay. You got a small piece, and I got a big piece. Would you like some of mine? Right? We're share. You can have some of mine. I got a big piece, and that wasn't fair to me, right? Or that wasn't fair to you. So I'll go ahead and I'll split it. So that whole philosophy is what supports this 1/2 of the sum, as far as would you share. So if we're going to call this arc A and this arc B, A plus B divided by 2 is going to be how we come up with the measure of angle X. And what's important to realize is that it's not about the angles, because the angles are guaranteed to be congruent. They're vertical angles. We know that they're congruent. It's not about that. It's about the measures of those arcs. All right, and while we were talking about all these crazy angle relationships, we took that center and we talked about what happens if you have a central angle and the vertex is on the center of the angle, then the arc and the angle are the same. And I want you to picture pulling this way out. You go from the center and you pull it way out. And once that vertex is on the circle, this angle becomes smaller. See how much smaller? In fact, it's half the size. Here's the thing. As you continue to pull that intersection out further from the circle, whether you end up with a secant and a tangent, 2 tangents, or 2 secants, the relationship is the same. It's the difference between the arcs, A minus B, divided by 2. So that sharing principle that we had up here, where we're taking the average, A plus B divided by 2. When you pull this angle so far out, it's A minus B divided by 2, smaller and smaller and smaller. This is the one we're going to be careful and watch out for, because these 2 tangents, a lot of times they like to make these problems trickier by only giving me one of these values, A or B. And I have to remember that it's 360 minus the 1 is equal to the other. So sometimes they make me solve for that other angle. That's okay. I'm smart enough. I can figure it out. No worries. All right. While we're talking about all these crazy stories that happens with secants and tangents, we're going to now talk about the segments. We're going to talk about when 2 chords intersect inside the circle. When I have 2 secants, a tangent and a secant. And if you're like, wait a minute, what about 2 tangents? Here's the story here. 2 tangents. The segments are always going to be congruent. All right, so here's this pretty cool rule that ends up happening. When you have an intersection inside the circle, it divides the chords so that their products are constant. It's kind of crazy to think about. So A times B is equal to C times D. So each of the product of the pieces is going to be the same. Cool fact that they figured out. if I take this intersection and I pull it outside of the circle, and again, whether I have two secants, a secant and a tangent, or two tangents, some cool relationships are happening, and it still has to do with the distance from the point of intersection to where this chord hits the circle. But because my intersection is outside of the circle, that distance to the circle is either this outside piece or it's this whole distance. So see how this chord intersects the circle twice here on A and B? This little letter A represents that distance from E to A, and this little letter B represents this distance from E to B. So it's still going to be A times B is equal to C times D, but instead of it being the two pieces inside the circle, it's this outside piece times that whole piece. That outer piece times your whole is equal to your outer piece times your whole. We're still talking about the distance from the point of intersection to where it touches the circle. And of course that happens when I have a tangent. That tangent is a squared value is going to be equal to this distance times the whole. And of course our two tangents are equal to each other. So we talked about that before, and chances are the back of your worksheet looks like this. Am I right? Does the back of your worksheet look like this?
Yeah.
With no work done on it? It's okay to be honest, okay? So what we're going to do is we're going to, instead of spending the entire time flipping, we're going to give yourself a note sheet. And we're going to condense everything that we've been talking about on one piece of paper. So we're going to start on this side when we talk about our angle relationships. So grab some colored pencils. Make sure you have a straight edge. And we're going to jump into giving ourselves a note sheet for us to think about and work with. All right, our number one relationship. It's all good. Our number one relationship that we learned out of the gates day one is this story about a central angle. So give yourself a nice central angle. Label it X degrees. Make sure you can see the intercepted arc because he's also a measure of X degrees, and you can give yourself a note that that is a central angle. Take your straight edge, and from that same intercepted arc, go ahead and give yourself an inscribed angle. By definition, an inscribed angle is one where the vertice sits on the circle. And you can even see it. Look how big this measure is. Look how small this measure is. Meanwhile, my intercepted arc has not changed. So what's this story here? X divided by 2, I think I heard. Or 1/2 x, right? However you want to put it down is fine. Now, something that's important on inscribed angles that I always like to give myself a picture of is the fact that, think about that movie theater seating. That same angle exists all the way around the circle. So it doesn't matter where I draw my intercepted arc. This is going to be the same angle as this is going to be the same angle as that. And we'll go ahead and make sure we know that's different from our central angle. So you should be able to look at that picture and be like, oh yeah, I recognize that from one intercepted arc, I can have many inscribed angles around the circle, and they have half of the degree measure of the central angle and the intercepted arc. Sound okay? Yeah? Okay. Along that same line is our conversation of when I have a tangent line, and that tangent line intersects with my circle and then a chord. So what ends up happening is this point of tangent C and the other end point of the chord create an arc around the circle.
How do you draw that again?
How do I do what?
Can you show me how you do that one more time?
I drew a tangent line and a chord. And I'm just coloring in the space around so I can make sure I can see it. The interesting story about this angle that's created and this arc here is that it's again half of that measure. And we can call this a chord. So if you want to, you can think about this as the ultimate angle, inscribed angle, right? If I opened up this intercepted arc so far to the other end point of the chord, that intercepted arc and this angle still have a 2-to-1 story. Now I like to call it half of the x and x, but it's totally fine if you want to call this y and 2y. Somebody said that they like that better because what they end up doing is they end up remembering that the total degrees in a circle are 360 and the total degrees in a line are 180, and that's where you get that 2-to-1 story. So maybe that might end up helping you out, whether you think of the arc double the angle or the angle half of the arc, whichever way makes sense to you is what we want. Check in with your partners and compare drawings. Make sure everybody's with me. These are too important to screw up. All right, ready? Next comes the middle school pizza problem. So go ahead and cut your pizza horribly unevenly so that any middle schooler would go home crying. It's not fair. I didn't get a big enough piece. Make sure that you recognize that these angles are not the conversation. Those angles I know are congruent because they're vertical. That's not what I'm upset about. What I'm upset about is look how big of a pizza this dude got. And look how small of a pizza this dude got. If we call this A and this B, then I know that my x degrees is equal to A plus B divided by 2. Because this nice middle schooler is going to share his pizza. So it's important that we take a minute and talk about, here is my intersection on the center of the circle, Here's my intersection of the chords on the circle. Here is my intersection inside the circle. Now it's time to draw our tangents and secants. So go ahead and draw 2 secant lines that intersect outside of the circle. Mark your arcs A and B. And you're always looking for your degrees. So this is when you have a secant and a secant that intersect in a point exterior to the circle. So the interesting thing when I'm inside the circle, it's A plus B divided by 2, sharing. And when I'm intersecting outside the circle, it's my big arc minus my little arc divided by 2 is equal to my x degrees. The further that x degree measure gets from the center, the smaller it gets. When it's on the center, it's equal. When it's on the circle, it's half. When it's in the interior, it's the average. When it's outside of the circle, it's the difference of the 2 arcs divided by 2. You can kind of see that progression happen. Next, we're going to draw 2 tangents, and this is the one where you're going to draw a little star to make sure that everybody knows that this one can be tricky. So here's 2 secant or 2 tangent lines. And remember, we're not talking about my angle or my segment length, we're talking about my angle measure. So here's our 2 tangent lines. And I'm still trying to figure out x degrees. And this one can be tricky because sometimes I get A and sometimes I get B, and it's still A minus B divided by 2. But sometimes they like to get tricky and rewrite one in terms of the other. So my B is going to be equal to 360 minus A. And sometimes my A is equal to 360 minus B. So they get tricky on this one sometimes. They give me just one number, and I got to know, oh, step 1, figure out the other arc. Step 2, subtract, divide by 2, and that's my x. So I've got 2 secants, 2 tangents. What's my next one? 1 tangent, 1 secant. You got it. So we'll draw 1 secant and we'll draw 1 tangent. We're still solving for x degrees. We still have our A, we still have our B, and it's still A minus B divided by 2 is equal to x degrees. So those last 3, the rules are totally the same. Sound okay? Yeah?
For that second to last one, is that the one that the denominator spot? Is
That's
that
a 2.
Okay.
That's a 2. All right. Moving on to the other side. Are we good? Now we're going to shift gears and we're going to talk about some of our segment relationships. And I want you to draw those 2 chords intersecting somewhere other than the center of the circle. But remember, we're talking about segments now and not angles. And we know that A times B is equal to C times D. The product of the pieces of those segments is going to be constant. It's a cool relationship they figured out. A times B equals C times D. The SOL loves this one. I think you'll see this one for sure. And again, when our intersection is on the center of the circle, then all of our radii are the same. So that relationship is still true. When our intersection is off of the circle, but inside, it's going to be the same. And this is the really crazy one. When our intersection is outside of the circle, nothing changes. So if I have 2 secants, I can still talk about A, and I can still talk about B. I can still talk about the distance from that point of intersection to where it hits the circle on both sides. So still, A times B is equal to C times D. And some people like to think of it visually. Some people like this formula. Some people like verbally outside piece times the whole is equal to outside piece times the whole. It's all about that distance from that point of intersection to where it hits the circle. And again, we can talk about this with 2 secants. We can talk about 1 secant and 1 tangent. Or we could talk about it with 2 tangents. So let's go ahead and draw each of those scenarios. If I have 1 secant and 1 tangent, my secant cuts through the middle of the circle and my tangent hits it once. My A So for my 2 tangents, there's no need to get super fancy. That was the one relationship we had a while ago. I just know, and if I want to say A squared is equal to B squared, that's fine because A is equal to B. So there's no reason for me to get too awful fancy with this one, because I can talk about A and B, and I can just say that those two values are going to be the same. It's not a lot to memorize if you see the patterns and the similarities. It's a couple rules that's important to talk about with each one. All right, so there's a couple extra things that we want to make sure that we include that you have down. Some additional relationships between segments and such. So this one's a little trickier. What I want you to do is I want you to draw two sectors, and I want you to try to make them congruent without using a diameter. You can go ahead and label them as congruent. And this counts as a segment relationship, because if the angles are congruent, so are the, what are these? Chords. And if the chords are congruent, so are the angles and the arcs. All three of them are related. So whether I'm talking about my angles, whether I'm talking about my chords, or whether I'm talking about my arcs, they all have that relationship. If you wanted to rescue your teacher from an avalanche, what three things do you need to know? Oh dear. Doesn't sound like anyone's going to be able to rescue me. What three things? If it's a diameter and it's perpendicular, it's a bisector. If it's a perpendicular and it's a bisector, it's a diameter. If it's a bisector and a diameter, then it's perpendicular. So you can remember how to save me from certain death. Here's one that I love. Go ahead and on this circle, draw 4 random dots anywhere. Take your straight edge and connect them. So the same thing we talked about before, where the distance around a circle is 360 and the distance of a line is 180, we can talk about if these inscribed angles are half of their intercepted arcs. This arc takes up this whole side of the circle, this arc takes up this whole side of the circle. So if the whole circle is represented, that means that those angles have to be supplementary. So opposite angles of a quadrilateral are going to be supplementary. So if you want to try to add some color, this angle X is defined by that orange arc. This angle Y is defined by this yellow arc. in our last circle, we're going to fit two ideas. Are you hanging with me? Draw a radius, and then draw a tangent at that pointed tangency, because every radius to that tangent is going to be perpendicular. And the last thing that we've talked about is if you have a diameter and that diameter defines an inscribed angle, doesn't matter where that angle is on the circle, it's guaranteed to be what? A right angle. Take a minute and go back through your drawings, label, check with your partners, see if they picked up something on your drawings that you missed. See if there's something that they included that you wish you added to yours. Go ahead, talk. Okay, now that we have those relationships, go back and revisit and try to see if you can identify as you approach a problem. Your first question is, am I solving for the angle or the segment length? Because the segment length takes you one direction, the angle takes you to another, and then agree with your group mates, oh, that's this one, oh, that's this one. Because if you can identify the problem, what you're looking for, then you can look at your notes to figure out what strategy you need to find it. So take a couple minutes and work on the back of the notes. On your mark, set, go. Let's just talk about number one, A, B, and C. Find the value of x, think angles. So these x values are going to be vertical angles. So that's fine. This is the middle school pizza problem. This guy got a bigger piece, 150 of the degrees. This guy only got 136. This dude's nice guy. He's like, that's okay, we'll share. So we'll average 136 plus 150 divided by 2 is 143. That is the measure of x. So this one's a little trickier because our x value is one of our arcs. So when we talk about a minus b divided by 2 is equal to 58, x is my unknown. So x minus 64 divided by 2 gives me 58. Step 1, when I'm looking at this, is to multiply each side by 2. So we want to make sure that you're used to that process. You'll be like, oh, I don't know how to solve that. Yes, you do. Multiply each side by 2. Cancel the 2 out. X minus 64 is 116. Therefore, x is 180. This last one, my two arc measures, 68 and 24. I'm going to find their difference. Divide by 2. And then that's my x. If my intersection is inside the circle, it's the average. If it's outside of the circle, it's my difference divided by 2. Again, not a spectator sport. You got to pick up your pencil and do the math. When you look at these three, we add one layer of trickiness. Here's the one I was talking about where they only give you one arc measure. All they did was tell me that arc BD is 110. Well, then I need to get major arc BCD. It's going to be 360 minus 110. Which gives me 250. Once I get 250 degrees for this major arc, and find their difference, divide by 2, and that's what gives me my angle measure. Here's the middle school pizza problem, but they made it one level more difficult. How? What did they do to make this a little harder? What did they do?
They didn't give you the interior angle that you need, so you minus it from.
Right. So they could have given us these two arcs to solve for x, or asked us for this angle. So they introduced another step. The SOL loves to introduce multi-tiers and steps. 96 is the degree measure of y. When I add the two arc measures, divide by 2, I get 96 degrees for y, and then I know that y and x are going to be supplementary. I went ahead and added my own variable. You can do that at any time. That's what helps you solve. This last one, again tricky, because instead of solving for the angle, they gave me the angle, and I'm solving for that arc measure. So I know 210 minus some number x is going to be equal to, or divided in half is going to be equal to this angle 72 degrees. Again, my first step is multiplying each side by 72, and then I solve for x. This one's tricky because you're like, wait, it can't be negative. You're like, it's not. We're good. Sound okay? All right. Now we're thinking segments. Now we're thinking segments. So 10 times x is equal to 8 times 5, not a problem. B is a big problem. I don't know why, but they gave us a quadratic that doesn't work out evenly. So what I care about for you guys right now is the geometry. Outside piece squared is equal to outside piece times the whole, and that whole is x times x plus 12. So that's a quadratic. I set my quadratic equal to 0 when I'm solving it. It's not factorable, so I have to use a quadratic formula. When I use the quadratic formula, I get this lovely value down here. We're not going to worry about that, because when you get something like this on any kind of assessment, they won't make you do the quadratic formula for now. Take a look at C. My outside piece times my whole, 12 times 12 plus x, is going to be the same as my outside piece times my whole, 15 plus 9. And I get a value of x is equal to 18. If you're not doing these, if you're just sitting there hanging out with no writing on your paper, it's going to be your job to go back and watch this video and figure this out. You cannot say no thank you. Not an option. All right, so you're standing at point Q, 9 feet from a large circular tent. The distance from you to a point of tangency is about 24 feet. Estimate the radius of the tent. So I know that my outside piece squared is going to be equal to my outside piece times my whole, and that's 9 times 9 plus r plus r. Somebody asked if they could draw a radius to the point of tangency and create a right triangle and do Pythagoras. Yeah, that'll work. 24 squared plus r squared is going to equal to 9 plus r quantity squared. You'll get the same answer.
How come you multiply 9 divided by 9?
Because this outside piece is times this whole.
Okay.
So here's my outside piece, and here's my whole. Okay? For you guys, when we ran the copies, the grid lines were too light, and they disappeared. So sorry about that, but you should be able to be fine with what you're drawing and doing and sketching for these notes. All right, so if we define a circle as all the points that are equidistant from a center point, we understand that that distance is our radius. So this distance here is going to be that center point. So if you think about my shoulder as the center and my arm as the radius, when I go to draw a circle all the way around, the circle is all of these points that are included. And there's an infinite number of XY ordered pairs that sit on that circle when we put it on the coordinate plane. The hard part about a circle is measuring the distance and figuring out where all these points are. They don't always match up on those integer coordinates with the grid lines. So mathematicians wanted to be able to put that circle on a grid, and they wanted to be able to come up with an equation and some predictability for it. So we're going to go ahead and let any XY ordered pair represent a point that's on the circle. The center of the circle we're always going to call HK. And when we go to write the equation of a circle, what they did was they're like, wait a minute, if the radius is that distance to that outside of the circle, maybe we can pull Pythagoras to help us figure out an equation for finding this point. After all, isn't this x coordinate and our y coordinate telling us our vertical and our horizontal distance? And if we do it vertically and horizontally, we're guaranteed to have a right triangle. And if that happens, why don't we call this A and why don't we call this B and call this radius C? And then we can have A squared plus B squared is equal to C squared. And then if you want to write an equation, call it x squared plus y squared is equal to r squared. So writing the equation of a circle is super easy once you think about that radius being the hypothesis of any xy coordinate on the hypotenuse of any xy coordinate. So you can go ahead and pick any xy and you can say, all right, I can have a radius and I can have an x and a y distance that I travel, and I can use this x and this y to find that r. So when mathematicians decided this was true, and they're like, oh, how cool this is that we can bring triangles in and help us write equations for circles, we're so excited. Somebody's like, hey, but that only works if the center of the circle is on the origin. What happens if we move it left or right or up or down? So that's when they decided the center of our circle was going to be these two variables, h and k. And that's when they're saying, okay, well, whatever the h movement is and whatever the k is, we'll correct it and bring it back to the origin. So these values that we get for our new center, h and k, represent what we need to do to account for that left, right, or up, down shift. So it again takes us back to lots of conversations about Pythagoras and about our distance formula. So that distance formula that talks about the changes in the x's and the changes in the y's, this is a negative, and how that gives us those distances. Some things to remember about our equations of circles. The coordinates in the center are naturally negative. They're set up with these negative signs. And I'll show you what that means in a minute. And this is something that gets kids all the time. The radius value is squared. So don't get that mixed up with doubled. Diameters are doubled. The radius in circles, the equation has it squared. So it really is this simple. Write the coordinates of the center and the radius of each circle given the equation. If I wanted to find my center, HK, I would take a look at how much x is changing. X is not changed at all. And my y was moved up 3, which means I need to account for that. So this negative sign in my center, when I have y minus a negative, that's how I ended up with a -3 for my center. My radius is going to be the square root of that value, or 2. Talk with your group mates about B and C. Go.
But it's positive. Because the equation is you see how here is adding, so it's negative. Here it's subtracting, so it's just
So the equation sets them up with negative. So I see an x minus 2, that center value is going to be positive 2. If I see x plus 3, that x coordinate of the center is going to be -7. My equation is what's going to get it back to the origin. My radius is going to be the square root of that number. That's there. All right, so let's graph one. A skydiving instruction school has a field with multiple landing targets. Each target is circle-shaped. A coordinate plane is used to arrange the targets in the field with the corner of the field as the origin. The equation, -8, -4, 9. What's my center going to be? +8, +4. So over 8 up 4, here's the center of my circle. What is the radius of my circle? What is it? 3. So here's how you graph a circle. Watch closely. Start at the center. Count up. 1, 2, 3. Draw a dot. Count down. 1, 2, 3. Draw a dot. Count left. 1, 2, 3. Draw a dot. Count right. 1, 2, 3. Draw a dot. Those are the only distances that we're guaranteed that we know. Everything else is on a curve and off of the integer. So what I want to do now is guesstimate and try to draw the best circle that I can. So with your group mates, go ahead and see who can get the best circle. And then I want you looking at Marika, Alex, Julia, and Caleb and see who lands inside the target. Go. So we'll go ahead and say that Marika and Caleb landed inside the circle. Way to go. Alex and Julia are still alive to talk about it. That's good enough. Anybody that jumps out of a perfectly fine plane ought to have their head examined. right? All right, so come on to the back. And I know for yours, you're missing the grid lines, so it's okay to estimate for this one. When we graph the circle, let's first talk about the coordinates of the center. What are my H and my K for this center? +3 and -1. So go ahead and count over 1, 2, 3, and down 1. It's okay if you're estimating. What is my radius? How'd you get 4? Yeah, so my radius is equal to the square root of 16. That's how I get 4. So when we graph that circle, count up 1, 2, 3, 4. Count down 1, 2, 3, 4. Left 1, 2, 3, 4. Right 1, 2, 3. Now this is a bigger circle. Definitely harder to get right. I keep trying to draw one arc consistently and spinning my paper. And look how terrible I did. That's a terrible circle. My diameter, your diameter equals double your radius. So diameter equals 8. What's that?
My circle.
Is your circle as bad as mine?
Hers is worse
Yeah.
than yours. Hers isn't even a circle.
Standard equation of the circle. If I have 0, 0, that means that neither my x nor my y are moved, and my radius squared. If you want to rewrite that, simplifying your radius, you can. Calling that x plus 5 is 20. X squared plus y squared is 25. Guaranteed the SOL asks you to write the equation of the line, given a center, given the radius. You would have no way of knowing how to do that yesterday, but today you're like, not a problem. It's not difficult. You just need somebody to tell you how to do it. This one's a little better. Talk about x squared, y squared, and what value you put in for your radius squared. Talk with your group mates about what goes in and completes that equation. Wait, what do you think? Go. Yeah, so that -2 in the naturally negative equation becomes positive. My 3 minus 3. This diameter is 14, which means that my radius is equal to 7. And don't forget that this is my radius squared. That's that tricky stuff. All right, I wanted to get to this one and make sure you understand how to do this. This point is on the circle. This is an XY ordered pair that makes it true. Here's the center. Let's talk about how to do this one. Ready? If I know that x plus 3 squared plus y minus 4 squared is equal to radius squared, nobody told me what my radius was. So I have an x, a y, and an r. 3 unknowns, I can't solve that. But they gave me values for my x and y. So if I put -1 in for x and +1 in for y, now I only have one unknown and I can solve for that no problem. So this is 2 squared plus -3 squared is equal to radius squared. So 4 plus 9 is equal to radius squared. 13 is equal to radius squared. That's all I need. Got?
Can you just do the distance formula between the first point and the second point?
Sure. You can either do the distance and figure that out, which if you'll notice is kind of like that, right? Except for there's no square root because I'm fine with it being square. So that's a great thought, Mason. You could put a Smarty up for that. So your final equation is x plus 3 squared plus y minus 4 squared is equal to 13. Mason's like, couldn't I use the distance formula? Absolutely. And I remember that my 13 is equal to my radius squared. Kind of cool. Here's your next one. This point is on a circle with this center. Go ahead with your group mates. Figure it out. Go. So the same process. I'm going to put my center point in. I'm going to take the one point that I know is the solution. And I'm going to solve for my radius squared, which in effect is the same as the distance. Solving for that radius. All right, so the next one's a little trickier. I have graph paper over here if you're frustrated by not being able to see the grid lines. If you want to draw a couple of light grid lines to help you out, that's fine. The whole idea is for you to be able to recognize your center and your radius of each of these problems. Notice it's a lovely hello to a lot of our perfect squares. So if you can get the center and the radius, that's half the battle. So the more you do it, the easier it is. Finding the center, finding the radius. So now what they want us to do is take a look at each line and graph the lines and determine whether it's a tangent or a secant to the circle in D above. So we just care about my orange one. So a little review of linear equations. My y-intercept of y is equal to mx plus b. So down 2 is my intercept and my slope is 1. Rise 1, run 1. Rise 1, run 1, rise 1, run 1. Would you call that a secant or a tangent line? That's definitely a secant line. Definitely a secant line because it intersects the circle twice. All right, y is equal to 2. That is a HOI. That is a horizontal line with a slope of 0. And a y in the equation. So what do we think about y is equal to 2? What is it? It's definitely a tangent line. Here's that point of tangency. X plus y is equal to 6. If I go to solve for y, I have a intercept of 6. And a slope of -1. Oh, what do we think? It's definitely tangent. Or definitely secant, right? And that's another secant line. So the question we're going to leave you with is how could you solve this without graphing? Any ideas?